Okay, ladies, here we go. We're going to talk about graphing a little bit today. It's very important to know how to do this for ecology, and I'm not going to keep up that voice the whole time. So you got this handout in class, and it has 6 different charts or graphs on it. These are extraordinarily important for ecology, and so with these we're going to talk a little bit about the graphs that you see that are used, as well as a couple of ways that scientists use to estimate how many organisms live in a given place or how many organisms are in a given population. So this very first thing you see here, graph number 1, is a very simple line graph, right? And what we see in this line graph is what's called a logistic curve. So logistic. Basically what logistic tells us is that we are going to have a section of the graph that's going to increase rapidly, but then what really makes it logistic is that it will level off at a given point and not get any bigger. This type of graph will show us the carrying capacity of a population, which, as you'll know from the notes, is basically the maximum number of species that a habitat can support and keep alive. We might see a few more, in this case rabbits, than this at some point, or a few less, but for the most part it's going to sustain this carrying capacity, and that's where the graph levels off. So for this graph, if we're asked here in letter B what the carrying capacity for these rabbits are, you see we've got basically time down here and you got number of rabbits over here. So what we're looking for is where this graph levels off. This graph levels off, as you can see, just above the 65 line right here. Right, so we can say that roughly about 67 is the carrying capacity for rabbits, because that's where this graph leveled off. So there's carrying capacity. Now the other question that you see here is, during which month were the rabbits in exponential growth? Exponential growth means growing rapidly. So the exponential part of this curve is kind of like here to here. Right, this is where we're exponential, we're growing rapidly. So the month at which we do that is going to be June. So again, logistic curve has sort of this S-like shape to it. It will always level off, that's what makes it logistic, and it will include usually an exponential part which grows very rapidly. And so again, in this case, the carrying capacity for rabbits shown to us is approximately about 67 rabbits. Alright, so graph 2 is another type of line graph. And this type of graph we actually call a bell-shaped curve. And that's because it sort of looks like a bell. You see, we actually are graphing 2 pieces of data here. We're graphing, with the thin line, we're graphing the average toe length, or length of the big toe. I know that's weird, but that's what we're looking at, in the year 1800, so that's this line down here. And then we are also looking at a graph of the same kind of data, but from the year 2000, and that's here our thicker, darker line. Now, the reason that you have a bell-shaped curve is because it allows you to see one thing, and that one thing that you're really interested in is the average. Right? So when we see a bell-shaped curve like this one, and we're looking for the average, we're going to look right in the middle. So wherever right in the middle of your bell is, that line's crooked, will be your average value. So let's look at some questions about this. First one, in 1800, about how many people surveyed had a 3-centimeter toe? So 1800, we're looking at this line down here, and we're looking for how many people had a 3-centimeter toe. So you're going to go to 3 centimeters, and we're going to get you right about there. Now that is going to be just under the 60 line, right? Is the answer 60 though? Because notice this is really important, in thousands, right? So for this, we could say, oh, there's probably about 57,000 people surveyed that had a 3 centimeter toe in the year 1800. Now the second question, how many people in the year 2000 had that 3 centimeter toe? So now we're looking on the other line, so we're going to look about right here, right? And we can say that roughly 10,000 or so people had that length toe in 2000. Now the next question is one that we haven't really gotten to yet, but it's pretty easy. And this data is showing us that over time people's toe length changed, right? In the year 1800 we had this graph, in the year 2000 we had this graph, so things changed. We say that this is the result of natural selection. So you might remember that from school before. This is evolution, right? Over time we're going to get changes in a species, and in this case we're talking about the length of toe. Now the last question is all about what I said earlier. These graphs show you the average. So if you look at where the middle of the bell falls, that's going to be your average for toe length. So in the year 2000, if we're looking at the thicker line, the average toe length was approximately, again this line is really crooked, maybe about somewhere between 4.5 and 5 centimeters. So we'll say 4.7 centimeters. And in 1800, check it out, their bell is still on the same plane. So we would again say maybe 4.7 centimeters. So even though more people had this given length of toe in the year 2000, the average toe length on both graphs is the same, because the average is the middle of the bell. Okay, so the third type of map I think you've maybe seen before. This is called an age structure diagram. Age structure diagram. We'll talk about these a little bit in class if we haven't yet. Basically, these are going to show you the given number of people or percentage of a population that is of a certain age group. And so you see here on the left we've got Mexico. Mexico, you'll notice, has a lot of people down here who are younger, not so many people who are older, right? And then we also split this, as you see, into male and female on either side going out. The United States is a little bit different shape, right? We still have more people in these younger ranges, but we also have more people in these older ranges than Mexico. So the first thing is just, can you read this graph? So letter A, in Mexico, what percentage of the population is between 0 and 4 years of age? So here's 0 and 4, so we're looking at the bottom level. And if it asks us about the entire population, right, entire population, that means that we have to add up both the boys and the girls here. So we have, not quite 8% of females are 0 to 4, not quite 8% of males are 0 to 4. So we can say roughly, 15 to 16% of the population of Mexico is 0 to 4. Then we want to look to answer the second part of the question at the United States as well, and we'll do the same thing. Add the girls and the boys. We have, about 3.5 and about 3.5 maybe. So we'll say for that one we're looking at about 7% of the U.S. population is that age. Now B says which population is growing the fastest. The key is to look for this type of age structure diagram. An age structure diagram that's fat on the bottom and tapers a lot is quickly growing, so that grows fast. One that's more regular or uniform, like this United States one, is more slowly growing. So the faster growing population in this case is Mexico. It's a terrible X. Now then the last question is also just a case of reading the graph. Which age group has the smallest number? And for that, we could probably safely say this group that is 80 plus. Right? I know it's arguable, this group's pretty small for the U.S. too, but we would say that the individuals who are 80 years and older is the smallest group. And that makes sense, right? An age structure diagram is going to show us who's more likely to die. And as you get older, you see smaller sizes in the population because older people are more likely to die than younger people. Okay, so this takes us into three more graphs or charts that show us ways in which scientists can estimate the number of organisms in a given place. We often call these sampling methods, because we're going to take a sample from the environment and then we're going to make an estimate as to how many overall creatures there are. So this first one, I'm going to kind of skip down to B here. This first technique is what we call the mark and recapture technique. Mark and recapture. Now, in this type of situation, what scientists will do is they will trap a given number of geese, mark them maybe by a tag on their wing or a tag on their leg, and then release them back into nature. Over time, then, they will collect new samples of the geese and see how many of those geese have one of those tags that they originally gave them. So for this given example, you see that we're looking at geese in northern Wisconsin. Ecologists originally marked 10 geese and then released them back into the population. Over a 6-year period, which we see over here, geese were trapped and their numbers were recorded. So we originally marked 10 different geese. And then in 1980, we trapped 10 and saw that one of them had a tag. 81, we collected 15, and we again noticed that one was marked with a tag. In 1982, we collect 12 geese, and we can see that one out of those 12 was marked with a tag. Then you can use this formula, combining all this data, and it will give us an estimate for how large the population size actually is. So total number captured would be all of these numbers. So if we add these up, 10, 15, 12, 8, 5, 10, we're going to get 60 were captured. We multiply that by the number marked, so that was our original value, so times 10, and then we would divide by the total number recaptured with a mark. So now we're talking about this data. So if we add up 1 plus 1 plus 1 plus 0 plus 2 plus 1, that's going to equal 6. If you do this math, 60 times 10 divided by 6, that equals 100. And so our estimated number of geese in this population is 100 geese, based solely on the number that we trapped and the number that had a mark with the second time we trapped them. Now here's the tricky question. If more of the geese found in traps had marks, would we estimate that the number of geese in the area was greater or lesser? So let's say that there are, we'll say what we have here. We have 60 geese that got trapped, and 10 of those had marks. If more of those geese that got captured had marks, we would assume that our population is probably smaller. Think about it this way. Let's say that I've got a big bucket of ping pong balls, right? And in that bucket of ping pong balls, I have 10 that are orange in color. And then I have, 20 that are white. If I ask you to pull out a ping pong ball, you've got 20 white ones, you've got 10 orange ones, I think is what I said a second ago. That's a total population of 30, right? Odds are pretty decent that you're going to pull out one of these 10 orange ones. But then let's say that I give you a new bin that has 10 orange ones and 500 white ones. Now the odds are much more likely that you're going to draw a white one out than you're going to draw an orange one out. So in this situation, since this population is only showing a 6 with a mark, that's probably a pretty big population. If, however, more of the geese that we recaptured were actually marked, we would assume the population is smaller because we'd have a better chance at finding marked geese. So the answer to this question is lesser. And if that still confuses you, we'll talk about that in class and do another example of this mark and recapture method. Okay, our fifth chart is, in this case, an example using mushrooms, but I'm going to skip again to B. We call this technique the plot sampling method. Plot sampling. in this situation, we can estimate the number of organisms living in a given area if the organisms are not moving around. So plot sampling works really well for things like plants. In this case, it's used for a fungus, but things that aren't mobile, like animals, because we need to be able to count how many are in a given space. So this ecologist, she plots a 10 by 10 area, so we got 10 squares this way, 10 squares that way, and randomly chooses 5 of the little spots in her plot. She goes to each of those spots and counts the number of mushrooms that she finds there. So in this place she found 5 mushrooms, here she found 2, here she found 3, here she found 2, and here she found 3. Now, the way that we can use this to estimate how many mushrooms are in this whole thing is by finding an average and applying that to every square. So if we start out and we find the average of these numbers that she collected, 5 plus 3 plus 3 plus 2 plus 2, all over 5 values, right? Find an average. This is going to equal 3. So what we're told now is on average there are 3 mushrooms in each of these squares. And if we've got a 10 by 10 grid, that means there's 100 squares. So we would take 3 times 100 squares, and we would estimate that we've got 300 mushrooms in this plot. Now what we actually say is that each one of these squares is called a quadrat. And this sampling method is used a lot in Kentucky because we document the trees that are in the forest. And so you might count, 5 trees in this plot. Find, using those numbers, the average number in each block, multiply by the number of blocks or quadrats, and that's going to give you an estimate of how many trees or mushrooms or whatever is there. And again, we call this the plot sampling method. Very last thing we're going to do here is just look at a data table. See a lot of data tables in ecology, a lot of data tables on the ACT, and coincidentally there will be some data tables on my tests that you're going to take. So we just want to look at this, which is a comparison of 2 populations here, a snake population and a mouse population. This means that we've got a predator that we're looking at, and we've got a prey species that we're looking at. So, just some questions using the data we see. First one, during which year was the mouse population at 0 population growth? What we're looking for is not going to be found on this table because I made typos, honestly. So what we want to do instead is we want to get rid of this 0 and we want to say which of these things is at negative population growth. And we're going to talk more about population growth coming very soon in class. But basically what we're looking for is if we're going to have negative population growth, that means that more are going to die than are actually born. So if we look down this graph, the only year where more died than were born is 1980. And so 1980 would be a year at which we have negative population growth. If we had 0 population growth, like the original question asked, we'd be looking for a situation where birth equaled deaths, and we don't see that in any of those years. Now the second question, what is the carrying capacity of snakes? The carrying capacity of snakes can be established by looking at the trend over the years and looking at how many snakes does this habitat seem to be able to support. So even though we had 2 one year, the habitat could probably support more. Even though we got up to 30 one year, that might be a little high. But notice how over the past 11 years in this graph, things started to level out around 14 or 15. So we can say that about 15, this must be swirly, about 15 snakes is the carrying capacity for this population. The next question is, what's the carrying capacity for mice? And quite honestly, this is a trick question. Right? Look at what we know. We know how many mice were born, and we know how many mice died, but we don't have a clue how many total mice are in the population. Right? And that's what we need to know. If we don't know the number of total mice, then we can't possibly figure out what the carrying capacity is. So don't be fooled here. Sometimes we're just given data like these pieces, and we can't figure out everything with it. Now, the last question says, what is the rate of growth for mice during 1970 and during 1980? In your class notes, we talk about growth rate. We talk about how that is birth rate plus immigration minus death rate plus emigration. Now, anytime that we are not given one of these values, which is the case here, we don't know immigration and we don't know emigration, you can ignore those. So in this scenario, the growth rate ends up being the birth rate minus the death rate. So for these mice, first we want to look at 1970. Here's our birth rate, here's our death rate. So in 1970, we're talking about 800 mice born minus 300 mice died, so we'd have 500 mice in 1970. Put 500 here. Now in 1980, we're going to do the same exact thing. So in 1980, we had 400 born, but 500 died. So that year, we're talking about a birth rate of 400 minus a death rate of 500, which is going to equal negative 100 mice per year. And this one over here would have also been mice per year. So notice you can have a positive population growth, which means that you're actually growing the population, or you can have a negative population growth. So I'm going to write that in over here. Negative population growth, where the number of your population is actually going down. So that completes this graphing practice handout. This honestly now becomes part of your notes, so you will be expected to be able to interpret these kind of graphs and do these methods. Please do not hesitate to bring this up in class and ask me about it more, and we can try to clarify anything that's still confusing to you. All right, thanks for listening.